Hello, everyone. Welcome to our webinar today. This webinar is being presented by Clean Energy Group, and the topic for today's webinar is Beyond Lithium, Part 1, Hydrostor's Advanced Compressed Air Energy Storage. Today's date is April 8th, 2026, and we have an excellent guest speaker with us today, but before I pass it over to him, I'd like to go over a few webinar logistics. All attendees are in listen-only mode, so your webcam and microphone are disabled. The chat function is also disabled, so if you would like to submit questions and comments, you can do so via the Q&A panel. We'll be saving about 15 minutes at the end of the presentation to address audience questions, so please feel free to type in your questions as you think of them throughout the presentation, and then we'll get to them at the end. Automated captions are available, and the speaker's bio will be made available in the chat as he's being introduced. And finally, this webinar is being recorded. We'll email you a webinar recording within 48 hours, and it will also be posted on CEG's website at cleanegroup.org/webinars. And with that, I'd like to pass it over to our host for today, my colleague Seth Mullendore.
Great. Thank you, Zareen, and thank you to everybody joining us today. We've got a good crowd. Hi, everyone. I'm Seth Mullendore, President and Executive Director of Clean Energy Group. For those of you that aren't as familiar with us, we are a national nonprofit. We work across the country to help ensure more affordable, reliable, clean energy for all. And we do that across a number of buckets of work. We focus on climate resilience and community health, distributed energy access and equity, energy storage and flexible demand, and fossil fuel replacement. Our topic today of Beyond Lithium, it really fits into a lot of those categories. Zareen, you can go ahead and go to the next slide. I'm going to get right to it. We're talking about non-lithium energy storage today, and we're going to have a series featuring different companies that are real leaders in this sector. A lot of them are long-duration energy storage companies, and that's going to be our first several webinars are going to focus on longer duration energy storage, but we'll also be looking at probably some shorter duration non-lithium as well. But the longer duration in particular, it's a real critical need for our energy system. And in many places, we're already there for needing longer duration storage. And if we're not there yet, in other places we will be soon. A lot of states are starting to procure longer duration energy storage, and a lot of them are looking at non-lithium to meet their goals. So our speaker today will tell you more about that. So just a quick introduction. We have Manuel Esquivel with us today, and he is the Senior Manager for Government and Regulatory Affairs at Hydrostor. So Hydrostor is an advanced compressed air energy storage technology, which you'll hear a lot more about in a moment. Manuel is he's focused on the Eastern U.S. markets and U.S. federal affairs and European markets. And I think we have a resource that has a longer bio from Manuel if you want to look into that. But with that, I will turn it over to our speaker, Manuel. Also a reminder to enter questions in the Q&A as you think of them, and we will be reserving a good amount of time at the end of the webinar today to address your questions. All right, Manuel.
All right. Well, thank you very much. And thank you to the Clean Energy Group for hosting Hydrostor today. Seth introduced me. My name is Manuel Esquivel, and I'm the Senior Manager of Government and Regulatory Affairs at Hydrostor, leading our regulatory work in the Eastern markets and some of the European jurisdictions as well. I've been with Hydrostor for about 2 years, and I'm based remotely out of Philadelphia, but I report into the U.S. headquarters in Denver, Colorado, but also into the global headquarters in Toronto. Before Hydrostor, I worked at Enel North America. I managed the regulatory affairs work primarily for the PJM region, including the PJM stakeholder process, but also ISO New England, NISO, and IESO in Ontario. Prior to Enel, I managed the district energy and microgrid programs for the city of Boston and worked at RMI on the passenger transportation sector in India, running some modeling for that. And I have a background in chemical engineering and public policy. So working at Hydrostor in this role, it's pretty special because it combines both of the roles, especially some of the experience that I have. I haven't worked in the mining sector. So it's pretty exciting, and I'm very excited to be here and uh, about to tell you more about the company, our technology, and our development projects. So quickly, briefly, here's what I'll be covering today. I'll tell you a little bit about Hydrostor as a company, and then I will give a very quick intro on some statistics on our technology, advanced compressed air energy storage. But before telling you more in depth about the technology or our projects, I'll take a step back and then go back and review why are we even talking about long duration energy storage and why LDES now. Then I'll move on to our technology, back to our technology, and explain it a bit more in detail and show some statistics there and benefits, including the economic and community benefits. And then I'll move on to showing information about our operating plant in Ontario and a few of our development projects, late stage development projects, and our pipeline. And then I'll end with, I guess, some sort of call to action. What are pathways for the development of LDES and advanced compressed air to be able to bring this technology to market to help us with the reliability and resilience of our grid. So with that, I'll start out Hydrostor at a glance. Hydrostor is a long duration energy storage developer, and we do that through our advanced compressed air energy storage solution. We have over 100 employees globally across our three offices in the US, in Canada, in Australia. We have one operating plant, like I said, that I'll tell you more about. Also, two late-stage development projects, one more sort of medium-term development, and in total, we have a pipeline of 7 gigawatts globally. So pretty excited about where Hydrostor is today. And we're able to do this work thanks to some key investors that have believed in our technology and helped us get to where we are, Goldman Sachs, and the Canada Pension Plan and the Canada Growth Fund. So we're very grateful for their support. Okay, so like I said, now I'm going to go on very briefly over sort of a few statistics on advanced compressed air. The first thing, and I'm doing this early on, typically I do it later in the presentation, but I just want to make sure that you maintain these in your minds throughout the presentation. These will be core things I'll be coming back to. But our technology is based on a proven technology. Compressed air already exists in the world. You'll see a little bit more about that, and we have improved on that existing system and basically rely on existing proven technology and equipment as well. Our type of long duration energy storage, there's different categories. We are in that 8 to 24 hour category, so intraday. One of the innovations compared to traditional compressed air is their flexibility in siting. So we don't rely on salt caverns, as some of you may have already investigated on compressed air and might know about existing systems in the world that are based on salt caverns. Well, we rely on hard rock. So that has allowed us to more flexibly look at locations around the globe and not just where there's existing caverns, but we make our own caverns in hard rock. We are a low cost and large scale system. So we'll keep coming back to this, but compared to other solutions, we're large. 500 megawatts is what you want to think about as. And you want to compare that to, we compare to 1 to 3 bigger plants in general. We're an emission-free operation. You'll hear more about that as we go. And we are a 50+ year asset. So when we're thinking of setting up shop in a community, we're not just going in as a new business that's going to be in the community. We're literally going to be part of that community because we're looking to make investments that will last 50+ years. So it's also an important component of our technology. Okay. Now with that, I'm going to take a step back and start covering a little bit more about why long duration energy storage. One key feature that we all know we're going to be needing more and more is flexibility and being able to more dynamically manage the supply and demand of our grid, especially as the generation portfolio becomes more diversified. You have all probably seen or heard about the California duck curve, which I guess now we are referring to as the canyon curve, due not just to how low it is dipping, but also how quickly the ramp up needs to occur. And we started to see these dynamics in other places, Arizona and other places, Texas, Hawaii, places with high penetration of solar generation. We're starting to also see it in ISO New England, where they're starting to count how many days there are with sort of duck curve types of days. So they're starting to see some of these dynamics. And long duration energy storage presents an important tool to help address this challenge in several ways. So first, especially now that we're seeing this canyon curves, LDES can store the generation that would otherwise have been curtailed and wasted to maintain grid stability, and then use it later when there's a greater need, greater demand for that electricity. Second, many of the long duration energy storage technologies, including ACAVES, is dispatchable on demand. So we can dispatch the stored energy to address that evening ramp. And third, it through these dynamics and what it's able to do, it can help relieve pressure on the inflexible baseload units that can't ramp down as quickly. Now, how does this all tie to affordability? As I was preparing these slides, I was going to have a slide just on affordability, but then quickly, as we're talking through it, affordability just comes through each and every one of these benefits and dynamics. And so really it's flexibility and affordability. And long duration energy storage in this particular flexibility case can help us just make the most of investments that we've already made for the grid, and be able to make the most of the generation that's been deployed without having to rely on more expensive, underutilized sort of peaking infrastructure. So that's sort of on the one hand. On the other hand, another benefit, another aspect, sort of issue to think about is resource adequacy and reliability. And this is a place where long duration energy storage will also provide important benefits. Across the country, you're seeing systems getting stressed and stretched to their limits. We've experienced that recently during storms Elliott, Uri, Fern. So some of you may have seen heat maps similar to what I'm showing on the screen, showing the PJM is one example that I'm more familiar with. Typically, they will show loss of load or unserved energy heat maps. Here, what I'm showing on the slide are heat maps from APS in Arizona. These are not LOLE or EUE, so in terms of those metrics, but it shows sort of it paints a similar picture, and it shows sort of the hours of system needs. And on the left, it's the figures from the IRP, which show long-term planning horizons, and I have the 2030 and the 2040 curve. If you go to the IRP, the link is attached to the title there. You can also see the 2035 curve. To the right, what I have is the similar heat map but from the RFP. The left is the IRP from 2024, the right is the RFP from 2025, and that one shows information for 2031. And then the keys are a little different, so you cannot compare them directly, apples to apples, but just sort of looking, you just have to do a little bit of work to sort of be able to look at it. But in general, what it paints the picture to show that there are system needs that extend beyond even 8 hours, even 10 hours. And those are spaces for both capacity and energy. And those are spaces that long duration energy storage, like advanced compressed air, can come in and provide benefits to maintain reliability. So why LDES now? I've say this often, LDES, long duration energy storage, is the future. It's a tool for the future of the grid, but the future is already here. And that's true sort of in two ways. One is LDES is already here, and we're not a technology of the future, but it's not developable. As you will see through Hydrostor's example, we're a commercially available commercially viable, low-cost solution available today. But it's also Elvis is here, the future is here. What I mean by that is we're already going through the transition of the grid. So the needs that we're going to need in that grid of the future, we're already starting to see now. The flexibility and reliability without sacrificing affordability is something we're deeply aware right now, given the constraints and the delays on new generation coming online, retirement of uneconomic generation, the unprecedented data center and other electrification load growth, driven also by more frequent extreme weather events. So long duration energy storage is a no regrets solution that we know we're going to be needing in the future and that future grid, but that we can deploy today to help us solve some of the issues we're already facing. Okay, so I've covered a little bit about the company, a little bit about our technology, and then talked about why long duration energy storage is important and why now. So now I will turn back into our technology and explain that in a little more in depth. To start out, I like to show that at the core of our technology is really air, rock, and water. So abundant materials that we are all, especially in the US, very familiar with from an industrial perspective. And this is basically what is at the core of our technology. And then how do we bring it together? Well, we use the air, rock, and water. We bring it together through conventional industrial equipment that has very stable supply chains and has also a long timeline of being used across different sectors in the mining, energy, oil and mining, and other industries. So it's equipment that we know that is readily available as well. And then on the cavern side, and I'll explain how we make our caverns a little bit, or how the cavern is part of our technology, but it's a core portion. It's a rock cavern. It's a core portion of our technology. This is also a known technology, making these caverns similar to the caverns that are used across the hydrocarbon storage industry. And we would pretty much use the same technology and contract with the same engineering firms that have this know-how. So even the cavern, which is the backbone of our technology, is it's a known technology. Okay, so how does it all come together? I'll explain the components and then also the process through this diagram. So you see that cavern right in the middle on the ground in the middle of the diagram. You can imagine we dig out this cavern and we flush it in with water. And that's sort of the starting condition of our plant. We then prepare a top energy plant that looks pretty much like other traditional plants. We have compressors, turbines, and a thermal management system. And how does it all work and come together? When there's excess electricity at lower prices, we use that electricity to run a compressor. The compressor then compresses the air down the shaft and into the cavern. And as the air is going into the cavern, that pushes the water out and displaces it to the surface reservoir that you see there to the right. During the compression step, compressing a gas generates heat. So we take that heat and save it in the thermal management system above ground. And we save it so that we can use it later on as the heat for the process that I will explain next. So with the heat saved on the sphere and the cavern full of air and the water in the reservoir, that's considered the charged state of our energy storage system, our battery. Once you're ready to use the air and regenerate the electricity, you open a valve, let the water from the reservoir flush into the cavern. That will push the air back out and up to the surface. At that point, the air will run through the heat exchanger, collecting the heat that we saved during the compression step, and then running a turbine um, to regenerate the electricity to go back out to the grid. So that's basically how our technology works. I have this slide with the process and the components explained on the left. And so once you get the slides, you'll be able to look at that. Or if I did not do a great job at explaining it, you can refer to this and study it again. Now, like I said at the beginning, compressed air already exists in the world. There's a plant in Germany, there's a plant in Alabama, and Hydrostor is a system integrator that took that technology and improved on it. And we improved on it in several ways. First, the traditional systems typically use gas to re-expand the air on the back end to heat it up to run in the turbines. Well, we have improved that system by saving the heat of compression to be able to use it as the heat then expands the air on the back end. We have increased the efficiency. This is one of the ways. Saving the heat from the compression just makes our plant a lot more efficient. So that's one of the major key differences that are allowing us to come back to the market with this technology in a very attractive way. By decoupling the need of gas, we have decoupled operating costs from being volatile. And we have also, as I mentioned, improved the flexibility of the technology by being able to site where there's hard rock and not just where there is existing salt caverns. And we have innovation. Now, this is one of my favorite aspects as sort of an engineer now in the public policy space. It's one of my favorite stories to talk about core innovation with patents and new technologies that are stable and come from existing technologies and being a system integrator in a new way. You don't always need to reinvent the wheel. You just have to use the wheel for new applications. Oh, sorry, trying to go to the next slide. Okay, so I talked a lot about our technology, gave a lot of different stats, but I want to make sure that we'll walk away with some key components of the Hydrostor's advanced compressed air technology. First, like I said at the beginning, we are large, 500 megawatts. Now we're large, but in a compressed footprint. We can generate 500 megawatts in 100 acres, which is a relatively small amount for the amount of power that we work with. Our duration. So we're starting out, our systems that are being developed in California and Arizona that I'll show soon are starting out at 8-hour systems. That's because those jurisdictions went out to the market specifically looking for those solutions. Now we could have started at 10, we could have started at 12. What's interesting is because of our technology, we're able to increase, we will be able to increase the duration of our systems at a low marginal cost. So even if we're starting out at 8 hours in California and Australia, the marginal cost to increase to 10 hours to 12 hours is very marginal. So it's an essential part of our technology. And then last is the efficiency. So the traditional systems have a very poor efficiency. We've been able to really bring it up to around 60 to 70%. Now, that doesn't look great by itself when you compare it to other technologies like lithium-ion, which is 80, 85 at times is what might be quoted. Now, the key difference here is that our plants do not degrade. There's no degradation of the cavern. In order for our systems to work, basically need the rock to be solid, and that is what drives pretty much the storage system. Then so there's no degradation. The efficiency that we go in on day one is the efficiency that we'll continue to have for the duration of the plant unless we make additional efficiency gains. But there's no degradation, which is a pretty core component of our technology as well. And then something that's very exciting about technology is the economic and community benefits. Like I said, we're thinking of ourselves as community partners, community members when we're going into a community, given the lifetime of our plants, of our assets. Our projects are long lead time projects, and they will employ thousands of construction workers throughout the construction process. And we have estimated that at peak, at a given time of the different peaks of construction work, there might be 750 workers being employed at the plant. Now, moving on to once the plant is operational, we will be employing around 40 full-time employees, and that's for the duration of the plant lifetime of 50 plus years. And then we also bring in a ton of community benefits in the order of $500 million over the project's construction, and then benefits throughout the lifetime of the plant as well. Okay, so that covers our technology and our benefits as well. So now I'll move on to talking about our existing projects. So Hydrostor currently has an operating plant, and this one is in Goderich. It's called Goderich. It's in Ontario, Canada. It's the first commercially contracted advanced compressed air energy storage facility. And this one helps us prove two things. One, it validates our innovation on the technology, the thermal management system. And because it's under a long-term contract, 10-year contract with the IESO, it also proves the ability to be able to operate in the market and buy and sell electricity with the Ontario market and be able to be operational in the market. This plant is our demonstration project, and so it's a little bit on the smaller side. It's about 2 megawatts. But again, it shows the thermal management system, showcases the thermal management system and the fact that we can operate in the market as well. We've brought groups in to tour the plant, and utility operators can see it and say, this technology sort of works. By looking at this demonstration plant, there is certainty that the technology works and is able to be an important asset for and participate in the markets, asset for the grid and participate in the markets. Now we have 2 projects in late stage development. One of the major ones is the one in Broken Hill in New South Wales in Australia called Silver City. This one is a project that is at the end of a transmission line supporting a mining community. The transmission system relied on 2 thermal units that announced that they would be retiring, and so the transmission operator needed to look for new solutions. One of the solutions would be increasing the size of the transmission lines. But given that this is at the end, the length of that transmission line would be pretty prohibitive. And so they performed a competitive bid, and Hydrostor was able to participate in that bid and secure a contract as the solution to be able to harden the transmission of the system there. And it's also a solution that's going to help bring in more generation locally, given sort of Australia's energy plans. It's really going to be able to help be able to bring in more solar and wind into the grid. And we have signed long-term contracts. And we've also been able to secure the permitting. We're looking to achieve financial close this year. Now, similarly, our project Willow Rock in California, it's exciting that this one's in the US. It's a 500 megawatt project in Kern County. It's northwest of Los Angeles. This one's coming in to respond to the needs that California is facing, that long duration energy storage can already help meet. And this one also has long-term contracts signed for a portion of the megawatts, and we're looking to achieve additional bids. And we're also slated to complete financial close by this year. And very exciting, we've completed the permitting for this project as well, the California Energy Commission permitting. So we should be in really good shape to move forward. Now, another project that we've been working on is Quinty in Ontario in Canada. This would be another 500 megawatt, 8-hour project. It's a little bit in earlier stages of development. And we're looking to work through the permitting as well as participate to receive offtake contracts this year. The permitting would be likely for next year as well. Sorry, coming back here. Okay. And on top of the existing project in Ontario and the 3 development projects that I mentioned, we have a pretty robust global pipeline as well, in the order of 7 gigawatts globally across North America, Europe, India, and Australia. Okay, and that covers our development projects. Now I'll spend a little bit of time talking about how to open up pathways and what do we need to be thinking about, especially here in the US, to be able to unleash investments for long duration energy storage and advanced compressed air in particular, to be able to start seeing these benefits today and starting to secure the grid of the future with no regret solutions. So the first thing that we need to be thinking about or looking at is setting up procurement targets. We should be looking at launching procurement targets and programs that properly value long duration energy storage, the benefits that we can bring to the grid. Those benefits are not currently being properly valued through the markets, and changing market rules to respond to needs and changes, that just takes a long time. So in order to secure the eldest technology to go into the grid and get started on the technology that we already need, and we're going to just continue to need more and more into the near future, is to start out with procurement targets, likely at the state and regional levels. And this is one of the strongest way in which we can incentivize development. New York, well, California has its targets, which has unleashed our development there. But New York is another jurisdiction that has a 20% carve out of their energy storage targets that we're excited about, and we have been collaborating with the jurisdiction, with the different agencies there to develop the strong program. Massachusetts is another jurisdiction that has gone in with come out with targets for long duration energy storage as well. And so other places can look at those 2 examples. Virginia as well recently. Well, the legislature passed a bill with long duration energy storage targets that we hope soon will be signed and approved by the governor. And so that'll be another example of a jurisdiction that has laid out procurement targets, long duration energy storage targets. A second important pillar is the contracts. And so as we're setting up these procurement targets and these procurement programs, we want to be thinking about how is this technology different from other energy technology, and what does the contracting need to look like, especially for long lead time assets like the advanced compressed air solution. And these are, air, rock, water, good old, in a way, good old American infrastructure, the way we know big infrastructure projects. So this is not new, and it's not new also in terms of contracting schemes that can really unleash this type of high capital cost infrastructure and long lead time infrastructure. So it's just a matter of creating those pathways and those specific contracts for this specific technology. So procurement targets first, and then set up a program that starts to look really at what is needed for the contracts and for the details of the program to really work out to unleash the infrastructure. And then last, one more thing that's very important is to start working on the system modeling and perform accurate system modeling that accounts for LDES under several scenarios and under several time horizons to really tell the story and see sort of what an incentive program can look like today to be a no regrets pathway to the future of the grid. But it's very important that we are able to very honestly and transparently are able to integrate LDES into these modelings and not preclude any sort of final answer, but really look at the data in the system and what it's telling us in terms of the system and the system needs. And the idea here would be really, let's look at what would be no regret solutions that we can start deploying and working on today. And I'm a true believer that incentive programs should be put in place to kickstart a market. And that's where we are right now in order to meet the needs that we're going to be facing for long duration energy storage that the DOE has released in its offtake documents and other jurisdictions that have done modeling. We really need to get started now for utilities, for agencies to be able to get the needed experience with this technology and to be able to prove the cases. And that's also associated with lower costs coming down the line, market changes, being able to make their way into sort of system operator market rules that then can continue to unleash the industry even more. So start with the targets so that we can unleash the no regret solutions. And this pretty much covers a lot of the information that I had for today. But just to recap, Hydrostor is a long duration energy storage company with our commercially available, low cost with economies of scale, advanced compressed air energy storage system. And we have a robust pipeline, 7 gigawatts, with advanced projects in the order of 700 megawatts with offtake contracts. So we're already needing to perform well to be able to satisfy those contracts. We have our one project, one pilot project, and then our commercial operating project that I mentioned in Ontario. It's innovation by being a system integrator and putting the pieces together that we know pretty well, air, rock, water, with infrastructure and equipment that we know in an innovative way. And it's backed by our the patents that we've been able to secure. Our 50 plus year asset, our efficiency is around 60 to 70%. But like I mentioned earlier, very importantly, our systems do not degrade. And that's different from other energy storage solutions. So that gives us a lot of stability in our economic modeling and 50-year sort of asset timeline. And the duration, 8+ hour. Again, going in with our late stage development projects at 8 hours. That's just because those jurisdictions were looking for that. We can start at 10, 12, depending on what the system needs call for. And the last thing I'll mention again is a reminder that we are a large scale project, 500 megawatts, in a compressed footprint of just about 100 acres. And with that, Seth, I think we would be ready for questions.
Great. Thank you so much, Manuel. There's just a lot of great information. We got a number of questions that have come in. For anyone who joined late, just a reminder that this is being recorded, and we will share the recording and the slides with anyone who registered for the webinar later on. It will also be available, the recording is publicly available as well to share with others after the webinar. Great. So, a lot of questions. I'm sure they'll keep coming in. Had a few related to the rock cavern. So there's a couple questions. One is, what are the geographic limitations? Like how widely applicable is this across different geographies? And specifically, someone asked, what are the best rock types? What are you looking for suitability for the rock cavern?
Yeah, thank you. So in terms of suitability geographically, we have done high level tabletop exercise and see that there is wide suitability across many regions of the globe. And so all the jurisdictions that I mentioned today, especially in the US, where I focus on the Eastern markets, are jurisdictions where we have seen there is geology that is viable for us to then continue to do the next stage of assessment, the feasibility assessment. Um, and this actually comes back to the second pillar of that ask when it comes to contracts and how to set up a program, especially for long lead time assets. I think given that it's a really large type of infrastructure, we need to stage gate our development in a way that makes sense for investment. Like, yes, we want to come in and invest and put in our dollars to continue to assess the opportunity, but we need progressively to get progressive market signals as we go. So we start out with a benchtop exercise to see if there is geology that is suitable, but then there would be later stages to further study the feasibility. But yeah, we know there is geology that we would be very excited to study with the right investment signals in New York. Well, in New York, we're already looking at a project there, but Massachusetts, Virginia, Maryland, and other jurisdictions. And then in terms of the specific type of rock, I would have to get back to you on that, but it's hard rock, essentially granites.
And related to that, there's a question just about water. Water availability is a concern in a lot of regions. You mentioned the project in California where that can be a concern. So, can you talk to me just about, availability of water? Is that, how much water does it use? And is there a large amount of evaporation, or does it mostly retain the water in the system?
Yeah, very glad this question's been asked. I should have mentioned that in my presentation. So the water that goes into our water reservoir is a one-time fill of water at the beginning of our operations. And then our system is actually a net producer of water. So any additional water that we might need to top up the reservoir, we would be able to get it directly from our from our uh, from our operation. So yeah, one-time fill that we're able to bring in on site, depending on the different conditions. The project in California will be different from the project in Australia, but it's a one-time fill, and it operates like regular water reservoir operations.
Great. So there's a question about just per megawatt hour, like what is the size of reservoir that's needed for a megawatt hour of energy? Like do you have the qubit, like what's the space needed, the volumetric space needed for a megawatt hour? Or if you know it in larger chunks, like what is the size of the cavern?
I know the cavern is approximately at a depth of 2,000 feet. But I'm forgetting the actual volume of the cavern. Let me try to find that real quick, so maybe we can come back to that as I address
Sure. And
other questions.
relatedly,
But
and
it's 100
yeah,
acres, and the
yeah.
eight-hour systems, you can imagine footprint-wise,
Hmm.
could be like a third of the 100 acres would be the footprint of the cavern.
Okay, when you talk about that 100 acres, um, so it doesn't take up the full 100 acres above surface. Some of that's the underground footprint as well. Is that correct?
So 100 acres would cover the top energy plant. It would
Hmm.
also house the water reservoir, but within that 100 acres is where the cavern um,
Got it.
would be as well. And if you need to grow the size of the plant, you can grow the cavern within that 100 acres as well.
Great. Yeah. And please feel free to be like, I'm not the right guy for this. Some of these are pretty technical questions that are coming up. I think this one's a more simple one. It's just that as far as the capacity of energy stored, that's just a matter of the size of the reservoir, correct?
That's right. And so the size, the capacity increases linearly or uh, with the size of the cavern, but the cost does not increase linearly. The marginal cost of increasing that is
Yeah.
pretty small.
So we certainly had some cost questions come up. One is
Okay.
directly that marginal cost. What's the marginal cost of adding more storage? But people also want to know what's the capital cost? What's the levelized cost of storage? So to the extent you're able to and willing to answer any of those questions, folks would love to know.
I think what I'm able to say right now when it comes to the cost is going back to thinking about the two projects that we have secured, the one in California and the one in Australia. We have been able to competitively participate in those bids and secure uh, being picked as the lowest cost projects in those two jurisdictions that went out looking specifically for those solutions for 8 hour type of solutions. So we've already proven that we are the low cost possibility to participate in these competitive bids as the lowest, um, yeah, the lowest alternative.
Great. So I got another technical question for you. Someone wants to know what the flow rate of the technology is, how much air is needed to make a megawatt hour of electricity. I'm not sure that that's something that you have at your fingertips or not.
Yeah, this is when I say, I did do chemical engineering, but now I don't do that. So sometimes I can step in and say, let me answer that question. But no, I'm just a policy guy. That's not a question I have an answer for right now, but happy to follow up on that and get information as best as we can.
Great. Yeah, I'm sure. I'm sure you love to hear from folks that want to get more information after this and direct their questions. Um, so when you're talking about the no degradation in storage, um, does that include the machinery or just the capacity of the reservoir? Like when you say it doesn't degrade over time, machinery can get less efficient as well. So what do you mean by that when you say there's no degradation?
Yeah, so there's definitely a need for the regular maintenance for all this machinery to have to take place, but the cost of that is not as high when it comes to sort of comparing it to degradation of other technologies. And I'm trying to remember what the lifetime of the machinery is, but it's the standard machinery that's used in oil mining gas with very sort of well-known maintenance um, protocols.
Right. There's a question, again, if you can answer this, of just who do you use as a supplier for turbines and compressors? What technology you mentioned off the shelf? Can you name partners that you work with on those?
Yeah, so very importantly, we recently announced a partnership with Baker Hughes, and that's a partnership for technology and equity as well. And I have a figure here. I think the partnership includes up to 1.4 gigawatts of equipment, and that's a partnership to support primarily initially our projects in California and Australia. So we've partnered with Baker Hughes, pretty important partnership there um, for our for our um, for our developments. And then also we have recently partnered with Hatch as well. They're going to be the partners for the front end engineering design for the project in California.
So, there's a lot of news about folks having a hard time getting a hold of power plants, turbines. Are you experiencing supply chain choke points? Are you having difficult time procuring what you need for the projects?
Yeah, right now we are, if everything keeps moving the way it's moving, and we're able to close financial close by this year, we'd be on time to get the systems up and running by the dates, the years that we need to have them operating per our contract. And that's where the partnership with Baker Hughes becomes very important and sort of that availability of working with them to secure the machinery and the equipment.
Great. So I'm interested, you talked about jobs creation. There's a question, what's the skill transferability from the fossil fuel industry to your technology?
That's an exciting aspect of our technology. Given with the renderings that I showed, our plants pretty much look like a traditional engineering plant, oil, mining, gas. So we're able to transfer jobs from that sector into our plant. And basically say, or my boss sometimes says, we can get people to walk across the street into our plants and with minimal training, be able to be operating these plants using the same skills that they had from prior experience. So
Great.
that's something we're pretty excited about, especially as we're, going into communities to help support communities, and if the job creation is a big aspect of that.
Great. This is a broad question, but what's your future outlook for development in the U.S.? There's a lot of lack of support for some technologies under the current administration. What do you think that the potential is for technology adoption and development in the U.S.?
We see it as pretty strong, and we're excited that the administration continues to recognize the importance of energy storage, and that the ITC, for example, was protected, and that is something that storage technologies is able to continue to capitalize on. Um, and yeah, we see a strong interest based on understanding of what the systems are going to be needing in many jurisdictions. Like I mentioned, New York with the energy storage roadmap and the information there on the long duration energy storage needs, starting with 8-hour systems, as well as the ISO New England's work on the dispatchable emission-free, sorry, the New York NISO, the dispatchable emission-free resources. And I think ISO New England's looking at those as well. Just the understanding of the system needs, it is widely recognized the long duration energy storage is going to be playing a role. So I think it's a policy question, how quickly we're able to use all this information that we currently have and start setting up the needed programs to unleash the investments and give us the right investment signals to be able to go in to a jurisdiction and start putting in our development dollars.
Great. Very specific question. Do you do work with tribal nations, or do you have any experience with working with tribal nations?
So I know that it's an important aspect of our project in Ontario. I am not as close to that project, so will not be able to speak to it. But yeah, that is an important component of one of our current development projects. And yeah, we would be excited to be able to bring solutions um,
Great.
and form partnerships.
There's some questions about scale, both on the can this be scaled down for a distribution, more of a distribution side application, and then on the flip side, is there any reason that it couldn't be scaled to 24-hour or 100-hour storage solution?
So when it comes to the scaling down, we are a utility scale, and we're going to be sort of operating at the transmission level. And the reason for that is the cavern primarily, but the rest of the infrastructure as well, it's high upfront capital costs. And so you need large systems to be able to get the economies of scale to be able to have a competitive project. The project in Australia is a 200 megawatt project, and that is just a very particular special case given that it's in a mining community and we're able to use an existing mining shaft. And then sort of that has cut down the costs, and there's other technical reasons why that project can be on the smaller side. But in the US, we're likely going to be that's why when I give the summary of the projects, we really want to be thinking about 500 megawatts as sort of the place. But yeah, other than that, we can grow, and we can grow from to uh, 8 to 24 hours. I think it's just a matter of the size of the cavern. So at some point, the size test might just become unfeasible.
Are there any safety issues associated with your systems?
Well, our systems are pretty safe. The cavern itself has to be stable and structurally sound and non-permeable. That's why we use hard rock. the water reservoirs are typical, and then those caverns have been used in the hydrocarbon storage industry to store different hydrocarbon gases, and we are storing air. So that's a very different type of gas. And then everything else is infrastructure and type of technology that's already used in other industries. The water reservoirs, there's industries with very stable water reservoirs with known civil engineering to make them be safe. And then the plants themselves, compressors, turbines, the way we use them in typical industry. So yeah, we're looking at a pretty safe technology.
What, how about permitting? I mean, I imagine this is, at least at this scale, it's not something that most jurisdictions have ever worked with before. So have you run into permitting difficulties, or again, is there familiarity because these types of storage has been used for hydrocarbons?
So I think when it comes to permitting, the maybe the biggest challenge is the fact that we're bringing in different solutions from different industries that are known and that have already been permitted, but we're putting them together in a different way. So I think it's just more going through the due diligence of what type of permits apply, or how do we put together uh, a package to be able to satisfy the different requirements. But yeah, like I said, we recently completed the California Energy Commission permitting for the Willow Rock project, and that has been a tremendous amount of work from the Hydrostor team, partnering with agencies at the state level and with wonderful consultants as well, to be able to partner and answer as many questions, both from the community at the local level, but also at the state level. And yeah, that's a success story that we've been able to permit in a state like California.
Right. Can you speak to a recharge rate? Is it the same as far as discharge and charging for recharging the cavern, or is it at a different rate of recharge? So it would take longer to recharge it than it does to discharge.
So I guess that's where the round trip efficiency starts to come into play. And so yeah, for an 8 hour system, you would use the RTE and calculate sort of how long it might need to take to be able to charge the system.
Just reading through, we've got a lot of questions coming in. Is there a concern around earthquakes? And you're doing a project in California, so is that a major concern for projects?
I would not be able to explain technically why not, but I have asked the question and I have to go back and remind myself of the answer. But I know that the answer has been no, that is not a concern for our technology. And I think it has something to do with the depth of the caverns and um, given sort of earthquake dynamics and the depth that we're talking about there, that's not a concern.
Great. We're almost out of time here. I'm gonna ask one more question. Just this question just about interaction with communities where these projects are going in. Have there been any common concerns from community members about these kinds of developments, things that you've worked with communities on when you're developing these projects?
Yeah, so we've had different experiences. No community is the same. So I think that is key, having early conversations, identifying sort of the right people, the right community voices to talk to, and pretty much of all and all the different types of stakeholders. So I think there's been experiences where people might just get the technology and are very excited from the get-go. Other experiences where people have a lot of questions, and rightly so. It's a big piece of infrastructure, but through a lot of engagement and a lot of communication with the community and very transparently answering all of the questions, we're able to mitigate that. Um, I don't work in the California project, but I did join one of the one of the meetings where the community members were the ones showing up to speak about them wanting to see the project come to the community. So that was pretty exciting, pretty special, and that's only achieved through the transparent, ongoing, available for being available for transparent communication and addressing the concerns that the community has. And something I think I really mean it when I say that we're thinking of going in to be community members. And so being able to sit down and think about what a community might need or want or what the concerns are is very important for us to be able to establish that stability through the lifetime of the community of the project.
Great. Well, thank you so much, Manuel. This has been great. I don't want to keep you any longer. I know we both got things happening here at the half hour mark. So thank you so much for your time. This has been great. And I do encourage folks to reach out. We'll be sharing again the recording and the slides with folks. So really appreciate everybody joining us today. I know, Zareen, we've got a final slide here about upcoming webinars that Clean Energy Group has coming up. So we've got a webinar in a couple of weeks on virtual power plants and energy justice. That should be a really great one. And stay tuned. We don't have this up for registration yet, but part two of our Beyond Lithium series is going to be on June 3rd, speaking with ESS about their iron flow battery. So thanks, everybody, and be on the lookout in your email inboxes for the recording and the slides. Thank you all.